Good morning and welcome to Flat Earth Debate. I'm your host, Nathan Oakley, and if you are new to this channel, or one of the 50% of the people watching who have not done so already, be sure to subscribe and hit the bell notification icon to keep up to date with the Flat Earth Debate. If you would like to support this channel, there is a link to Super Chat that runs alongside the show while it is live. And most importantly, if you would like to join the debate with the page you are currently watching on mute, simply click on the link in the info box below this video to join the show and express your views on the shape of the Earth. There are, however, a couple of rules in the Hangout. Number 1, please do not swear. If you do, you will be ejected. And number 2, if you are ejected, please do not try to rejoin the show using sock accounts. You will be warmly welcome back on the next stream. With that, I'm going to transition across to my photographs and share the show on Facebook, Skype and Twitter, and I would encourage anybody who is currently in the live stream to please also do the same. Please share the show on social media. One more time, if you're new to the channel or you've not done so already, be sure to subscribe and hit the bell notification icon to keep up to date with the Flat Earth Debate. Shout out to Vinegar Strokes. Pleased to have you in the live chat. Good to see you. Good morning to you too. Please share the show. I've just shared the show on Facebook, Skype and Twitter, and once again I would encourage anybody who is in the live stream right now to please also share the show. Smash that share button and increase the live audience. Increasing the live audience also increases the chances of having a more diverse panel, so it's one of those things that I will pester the audience to share and get this video out to as many people as possible, as I say, to increase the diversity of the panel. If you are new to this channel or you have not done so already, be sure to subscribe and hit the bell notification icon to keep up to date with the Flat Earth Debate. If you would like to, as we've just been joined by Mate4, I might keep this brief. If you would like to support this channel, there is a super chat that runs alongside the show while it is live. And if you would like to join the debate, as Mate4 has just done, simply click on the link in the info box below this video. Remember the 2 rules: please do not swear, and if you are swearing, you'll be ejected, but you will be warmly welcome back on the next stream, so please don't try to rejoin the show using sock accounts. And with that, I'll make my first introduction to Mate4. How you doing, Mate4? Oh, you're a bit low on my desk. Bear with me a second. Excellent. Good to have you here. Bear with me just 1 second while I sort out a minor issue. It might help if I actually had all my monitors on and I could actually hear the guests, but hopefully now I can, now all my amps are on. Happy days.
Hey, mate.
Good to have you here.
I was just watching, I'm not sure, it would have, the earlier debate, just the last debate, because I missed it, actually. I was in bed, and you guys going on about pressure. It was a big pressure talk, like the vacuum dealio.
Yeah, it was one of them. Right at the beginning of that merry-go-round, I tried to interject and say, look, it's about the pressure differential as opposed to just the pressure on one side or the other of whatever wall or whatever barrier. But that's kind of where the conversation went for about 25 minutes, and it was amusing, so I just sat and let it roll, and then eventually they did. I think it was Anthony Riley that finally got it to the point where they're like, well, there's a pressure differential. It's like, yeah, right, we're back on track now. But yeah, there was a good solid probably 25 minutes of just merry-go-round of nonsense, wasn't there?
Oh, it was all right. I was surprised to see David actually, at one point there, David answered quite well, and the question that curved water throughout was something like, okay, if you've got 15 psi in the ISS, is it going to implode or explode? And David was like, bam, it's gonna explode. And I was like, that's actually right. I think that would be right, because the whole tanker thing. Wow. Like, basically, it's the same as when you have bottles, like plastic Coke bottles, and you leave them out in the sun and they just sort of crush down. I guess, having the sun there is a bit of a heat factor, is just burning up all the stuff inside it and evaporating things, so it just crushes it down and loses its atmosphere inside and sucks. But yeah, I guess the ISS would have to be designed to not explode, because if the pressure's inside, where you've got all your pressure and your oxygen, then it wants to get out. Really, it doesn't want to. Yeah, it's trying to get out to that vacuum, and I believe there would be some sort of not so much a sucking on the how do I say, I'm sure there would be certain pressures on the ISS that would be, it'd have some forces and almost like you would think that it could, hey, it's the physicist dude.
Been joined by Paul. How you doing, Paul?
Yeah, it's Paul.
Yeah, hi, Mate4.
Hey, mate.
Yeah,
how you going?
Us down in Australia have to sleep sometimes, don't we?
True.
Yeah, for sure. So.
What time is it there, Paul?
Just looking at my clock, it's 20 to 10 in the evening.
It's about the time I start the evening show here is about that sort of time in the UK.
Well, yeah.
Sorry. Yeah. So they were arguing, would it implode or explode? La la la.
Yeah, completely missed the last one because I was so stuffed that I had to sleep. So what was the last one about? What was this talk about pressure?
Yeah, I was just having a quick listen to it, and it's someone brought up the question of if the spaceship's out there and it's pressurized, the question originally was, oh well, we're gonna have to have a pretty good spaceship to hold that pressure kind of thing, and the guys were like, it's like 15 psi, it's like a bike tire or something. So that sort of got wafted off. But But then they started sort of going into the whole like structure of it would have to be built so that the pressure that's in there wouldn't like be, well, the way they were putting
It's
it
not-
was
It's not like submarines where you have to stop the pressure from pressing it inwards. You have to
Yes.
stop the pressure from pressing it outwards, which is a much easier task to achieve.
For sure. And someone did say like that, a vacuum is technically 0 psi. Is that correct? Like it's just nothing.
Yes, that's correct.
It makes sense.
Yeah, that's right.
So yeah, it's not like it goes into negatives or something.
Yeah, you're not fighting against
No.
the vacuum. You're fighting against the pressure inside the vessel, which is trying to escape to the vacuum. So it's
Yes.
that pressure pushing outwards.
So technically,
Yeah, that's
it's kind of weird because like, if there was a hole in it, from the inside, it would sort of look like it was sucking, but from the outside, it'd just look like it was spewing out sort of oxygen gas or something.
Yeah,
So,
that's
like,
right. One of the biggest misconceptions is that vacuums suck. Vacuums don't suck. Vacuums are simply just an absence of everything. They can't do anything. There's a little experiment thought experiment you can use to illustrate this fact. Here on Earth, you get a syringe and you take the needle off, obviously. And if you put your finger over the end and try to pull the little plunger out, it's very hard to do, isn't it?
Yes, sorry. I think I get what you're saying. Yep.
Yeah, but if you were to try the same thing in a vacuum, you would have no difficulty whatsoever pulling that plunger out.
But because there's no area anywhere.
Because there's no pressure pushing the plunger back in. That's the point to make, is that we have difficulty doing that on Earth here, not because the vacuum inside is sucking the plunger in. It's the weight of the air and the atmosphere pushing that plunger in. It's the atmosphere pushing on it that stops us from pulling it out. Okay? Not
That's
the
kind of
vacuum
weird.
inside. Yeah.
That's like if you were in the vacuum, just say your house was in a vacuum, and then you got a syringe, and there would be no oxygen in that syringe at all anywhere, nothing, even gases.
Nothing.
or
That's
anything.
right.
So you could just sit there like holding your thumb on it, like holding the pressure and just moving it in and out, really. That's how I feel.
That's right. That's correct.
Yeah. It's like
Yeah, that's precisely correct. Yes.
It's probably
It's a
easier
con-
to explain if you use water. So if you're using a water-filled container and it's a pop bottle, forget about the vacuum for the moment, just for the simplicity of this explanation. But if you've got a pop bottle and you over-pressurize it, it will then explode outwards. However, if you suck all of the air out of that bottle, the pressure on the outside of the air that sat on that bottle is the thing that will crush that bottle. So I will introduce you in a minute, Sleeping Warrior. But Sleeping Warrior did 2 demonstrations. One was done by, I believe, Mythbusters, and they took a pre-prepared, let's call it pre-prepared container truck. So they damaged it in advance of doing this so that it would crush with the atmospheric pressure. Because obviously a container truck is designed...
I've seen that episode.
Yeah, but it's obviously...
They tried it without damaging it and they couldn't achieve it because
of course,
it was
because
built
you'd
so well.
expect a tanker truck to withstand atmospheric pressure, let's face it. So they'd have to do something to make it achieve that effect. But that showed exactly that. So you remove the air from the container and the pressure of the air on the outside crushed it in. And then he showed the opposite of that, which was a plastic bottle in a vacuum, which was at about... the inside pressure of that bottle was about 15 psi. It was placed in a vacuum, and sure enough, the top popped off outwards, so it exploded outwards into the vacuum. Anyway, we've been joined by Sleeping Warrior. Sorry, I will let you talk again, Paul. We've just been joined by Sleeping Warrior. Pleased to have you here, Anthony.
I was just listening to Paul spouting rhetoric. Can you prove that it's not the vacuum that's sucking it in, that it's the atmosphere of things that's pushing it out? Because you were talking about the needle and the sucking of when you stick it on, I think you said on your skin, and you pull the plunger out, and you said that it's not the pulling of the plunger that's difficult because of the vacuum that you're creating. It's because of the pressure of the atmosphere that's pushing against it.
Is that correct?
What can you prove
that's correct.
Can you prove that it's the atmosphere that's pushing against it that's making the plunger difficult to pull out?
Yeah, these experiments can be done in a vacuum here on Earth, and it's been done thousands of times. You can put a similar sort of thing inside a vacuum chamber, and you can seal the end of the syringe and pull it. It can be demonstrated quite easily.
Okay, can you do that for us?
Well, I can't do that here right now, no. But you can. It has been done, and it is a well-known thing.
Well, so you say, but like Nathan just said, we watched 2 videos last night. One was the tanker imploding, and I didn't realize it was pre-damaged on purpose to make it do it. And then the other video that we watched was the bottle, and there was a small plastic bottle that, as the pressure or as the vacuum was created on the outside, it burst. Now the question,
that's correct.
The question is, does it burst because of the internal pressure within the bottle, or does it get sucked out?
Yes, it does. No, it bursts because of the pressure inside the bottle.
Wait.
The reason why, do you understand what pressure is created by?
Yes. But can you demonstrate that it's the pressure that's inside the bottle pushing it out? Because I assert to you that it's the vacuum that's pulling it out, not the internal pressure pushing it out.
Well, you're wrong, because forces are what make things move. Okay. And a vacuum containing nothing in it cannot exert a force on anything.
So
it's the molecules. It's the molecules inside the container. If we're talking about the one that's got the fluid inside and the vacuum on the outside, it's the molecules inside the container hitting the walls of the container that exert the force outwards on the container. And if there's nothing to oppose that force on the outside, then of course you've got the force pushing one way. You've got nothing to oppose that force, and that is why it explodes.
So you say, but you're unable to prove that. You're unable to prove that.
Well,
wait. The video that we played last night showed that it was the bottle top that burst on the. Basically, it was like a bottle of pop bursting on the inside. Your position is that it gets pushed from the inside. My position is it gets sucked from the outside. And
what's sucking it?
The vacuum itself. So basically, what your position is.
The vacuum's got nothing in it to suck.
Right, exactly. So your position is that the vacuum. Wait, your position is that the vacuum is not a negative value. My position is that
that's correct.
My position is that the vacuum is absolutely a negative value. So what I want you to demonstrate is how it's the positive value pushing it out. How can you prove that that's the case?
Well, Paul, can I try and just address this for Anthony? It's as likely when you reverse the situation to say that the atmospheric pressure is pulling the pressurized pop out of the pop bottle, and the atmospheric pressure is not sucking the pop out of the pop bottle. You know, it's the same principle in reverse. You can't assert that pressurized pop bottle is being sucked by atmospheric pressure. It's nonsense.
Well, you can do if you have a vacuum meter that tells you what the pressure of the vacuum is.
That's why I excluded the vacuum from that example. So at atmospheric pressure, if you pressurize a bottle and you overpressurize it and it explodes, your assertion would dictate that the atmospheric pressure has sucked that pop out of that bottle, and it hasn't. It's the pressure inside the bottle that has forced it out, and the same applies in the vacuum. The pressure inside the bottle has forced the lid off when the outside pressure stops counteracting the inside pressure of the bottle. So when you've got no vacuum, the pressure is counteracted. So the outside pressure of the air inside the bottle, well, the outside pressure of the air is pressing on the bottle equally to the inside pressure of the bottle pressing outwards. So the two are at an equilibrium. When you remove the air, there is no longer an equilibrium. There is an imbalance. The imbalance being on the inside of the bottle, and that imbalance forces the top off.
Yeah, but are we on about in space here, or are we on about on the ground?
Yeah, in that example, the imbalance is in a vacuum. So you have a pressure equilibrium between the bottle and the outside air pressure. So the pressure inside the bottle with the cap on is the same as the air outside. So the two balance, so the top doesn't come off. When you remove the air, the inside air inside the bottle with the cap on is greater than the outside pressure. So it forces outwards, forcing the top off.
So is your position that it's the vacuum sucking the top off, or is your position that it's the content?
No,
absolutely not. It's the pressure inside the bottle. The pressure is inside the bottle forcing outwards because there's nothing counteracting it.
No, it's the other way around. The vacuum is a negative pressure and it's pulling the top off.
No, can we knock that one on the head straight away? There is no such thing as negative pressure. Pressure is created by molecules bumping into things. You cannot have negative bumping into. If you've got an absence of something, as in a vacuum, you cannot have molecules bumping into anything. There's no such thing as a negative pressure. You can have negative relative pressures,
Yes.
You can have negative relative pressures. If you define atmospheric pressure as 0, then lower than that would be negative.
And it's
But
for
you
that
cannot,
exact reason. That's for
but
that.
you cannot, let me finish, please, but you cannot have an absolute negative pressure, okay? Because an absence of something means 0 pressure, because it is unable to create pressure because it's an absence of things that could provide the force, okay?
No,
Now, in the,
no.
Yes. In the situation with
Absolutely
the
not.
pop
You've got
bottle,
it the wrong way round. You're telling people lies. You're either not getting
I
this right.
beg your pardon.
No.
I am not telling people
Yeah, you are.
lies.
You've just said
no.
it yourself. You've just said it
wait.
yourself.
Can you let me finish, please?
No, because I want to interrupt you because you're telling people lies.
Well,
That's wrong.
because I
can I have a
haven't. No.
Right.
All right.
Because he would be on
Okay.
point.
It's the relative pressures that's the issue. So if you have a big difference in the relative pressures, instantly it's going to equalize the minute it gets the opportunity to do so. So if we put let's say a bottle of pop, that bottle of pop went inside the tanker, and then we sucked all the air outside the tanker, and we know that when there's no bottle in there, we know that the tanker will crumple eventually. But when you put a bottle of pop inside there,
That's under the atmosphere's pressure, though. Under where
so,
we live.
So they say, but
You've created a
when you remove
vacuum
all the
inside
air,
our atmosphere.
you're creating
It's
a relative void.
pressure.
You're creating a relative void in relation to the atmosphere that the tanker sits in. So what that then does is, you're saying it's the force of the pressure of the atmosphere pushing against it. I'm saying it's the lack of pressure on the inside that's pulling it.
No, vacuums do not pull.
Yes, they do.
Okay.
Of course they do.
No, they do not. Can you let me explain, please? A force must be created by something. In the sense of pressure, force is created by molecules bumping into things. Okay? Molecules bump into the walls of the container and exert a force on the walls of the container. That is what the pressure is. You cannot have a pressure if there are no molecules to bump into anything. A vacuum does not have an absolute pressure because of the very fact that it has no molecules in it to create a force. Okay? So the pressure inside is created by the molecules bumping into the walls of the container. They push outwards. There is nothing on the other side in the vacuum to push back. If you are claiming the vacuum is sucking, then you have to explain what is pulling.
You're talking about in space. He's talking about when you're out in space and you're in your space.
It's the relative difference between the two pressures that's pulling it. You're saying it's
pushing. That's right. A vacuum is 0 pressure. Inside is a positive pressure. It's the pressure differential. Yes, that's right.
Absolutely.
But
it's pressure differential.
It is not the vacuum sucking. It is the pressure of the molecules inside bumping into the walls of the container that create the pressure inside that makes the bottle explode.
How do we prove
They
that?
are the things that are bumping against the walls of the container.
How do we prove that's true? Do we rely on logic and reason?
Proven. Unfortunately, there are people that make gauges to measure pressure differentials. You know, this is
exactly.
a fact.
Yeah, and when we measure pressure differentials, it still doesn't tell us which force is pulling or pushing.
But
there is nothing to pull in a vacuum.
This is it. This is the pressure differential is based on what you have on one side of the barrier and what you have on the other. This is where Paul explained that you can have a negative overall difference, but that's based on having one side pushing harder than the other on one side or other of the barrier. When you go out into a vacuum, it totally changes because there's no pressure reacting backwards. So once you pop that balloon in a vacuum, all of the air or molecules or whatever are inside that balloon will disperse through the container and create an equilibrium. But if you were then to put an even higher pressure vacuum in a balloon into that now lesser vacuum, that would then have the same effect if it was at a higher pressure, because the difference at that point would be higher in the balloon than in the overall box.
So how do we know which one it is? Because Paul claims that it's the pressure inside pushing out, and you agree. I claim it's the lower pressure on the outside that's pulling it out. It wants to burst it from the outside.
And that's true until you get to 0. That's true until you're in a vacuum.
Sorry, can I talk? Pressure is created by molecules bumping into things. That's what pressure is. Pressure is created by the force of the molecules bumping into things. If you don't have molecules, you cannot have pressure.
But can you prove that it's the internal pressure that's pushing it out or not? I know you described
because there are molecules inside and there aren't molecules outside.
Right, but there's pressure outside. There's a pressure difference outside.
Yes, right. Of course there's a pressure difference because there are molecules inside and not outside.
Yeah, but I'm not saying it's the molecules causing it. I'm saying it's directly the pressure.
I'm sorry, but that's what the definition of pressure is.
Well, can it be demonstrated that that's the case, though?
What do you mean? You put more air inside something, you get a higher pressure because there are more molecules bumping into the walls of the container.
But how can you prove that it's the pressure inside pushing it out? How can that be proven? I don't want definitions or explanations. I want the proof.
Anthony, this is logical reasoning. You put more air inside. I beg your pardon.
Logic is not proof.
Okay, I blow up a balloon to a certain size. I blow it up even bigger, and it has a higher pressure in it. I've put more air in it, and therefore it has a higher pressure in it.
Yeah.
What caused the higher pressure?
The pressure itself. You put more pressure into it.
What caused the higher pressure?
You putting more air into it.
Yes, I put more molecules in there. More molecules are bumping into the wall of the container, causing a higher pressure.
Yeah, but that still isn't answering the question.
Pressure.
The question is, how can you prove that it's the internal that's pushing out rather than the outside that's pulling it apart? How can you prove it?
Well, that's dependent
because
on the
there is nothing. Forces are created by things. If there's nothing outside, what is causing the pulling force?
It's the pressure.
There is no pressure outside. There is nothing to create a force on the outside.
Right.
Forces are created by things. The molecules on the inside of the container are what provide the force. I am.
Prove that it's the inside pushing and not the outside sucking.
Because there are molecules inside and there are none outside.
Can you prove it to be true, though? I know what you're saying. And I'm saying it's not right.
Joule Thomson effect, or you can read the kinetic theory of gas expansion in a vacuum for further details. Paul is 100% correct.
Prove it then. Let's see the evidence that proves it's the inside pushing.
It's already been proven. I just cited the actual experiment that proves it. It's called Joule Thomson effect.
Right, so can you show it on screen?
Learn that on your own time. You're not paying me to be your professor. These aren't things I have to prove to you. I already stated the fact that other people can actually verify right now. So it's not up to me or you if we're right or wrong in this debate. It's up to everyone else. So stop with the old, you have to prove it to me thing. I prove it to the audience. Joule Thomson effect. Hardest of the audience figures it out, then you lose. It doesn't matter if you figure it out or not. I don't get mad at a horse if I tell a horse a joke and the horse doesn't get the joke. It's my own fault. I have to realize that the horse is just dumb.
No, but the assertion is it's being pushed from the inside. And he can't prove it or won't prove it because there's money involved. So if
you can talk all you want after that, but the Joule Thomson effect debunks everything you're saying. Sorry.
What did you just say?
Joule Thomson effect.
Joule.
Joule. Thomson. THO.
So to save you the risk of money side of it, so let me type it in the side chat and you can tell me whether this is right. Joule Thompson.
Just ask Google and they'll spell check it for you.
Right, so let's try and prove your assertion to be true then, because you can't be bothered to prove it. Usually the burden is on he who asserts. For some reason now it seems to be acceptable that you're not prepared to prove your assertion to be true.
You talk a lot, dude. I swear. And you don't
so now you, Anthony, have to prove that the vacuum sucks.
No, you're the one that's saying it's being pushed from the inside. I'm asking you to prove it, and now for some reason it's to do with money.
And you're the one. And you're the one.
Stop talking over me. I'm speaking at the moment.
Oi, can I have a chance for once? You're
the one that asserts that the blue pushes from the inside. I'm asking for proof.
And you're the one asserting
won't do it because of money. So if we now have to prove your claims to be true,
one little chance, even though I am on your side, technically. Okay, can I talk? I've been waiting for like 10 or 20 minutes or something. Seriously, I have a question related to these pressures, and like it might answer it a little bit because okay, say I've got a bottle, you close it pretty damn tight so the lid isn't going to go anywhere. And then you've got that equilibrium that Nathan was talking about, right? Where both pressures are the same now. We're at sea level. Just imagine that. And anyway, so it's got nothing to do with, well, it kind of does actually. It's got to do with we're at sea level and the atmosphere around us is around that bottle. Okay, so I want to ask Paul, what's the go with the internals of that bottle? Like when the sun hits it or whatever, is there like some sort of, I don't know how to explain, is it called ionization or something? Like what goes on inside that bottle that causes it to implode instead? Because you guys are talking explode. I want to understand the implode and then how the heat on that bottle. Have you seen that happen before?
You'll have to explain that experiment to me. Explain exactly what you do and exactly what happens.
Have you ever just seen an empty Coke bottle implode? Like they just like the sun sucks all the air out of it or something?
No, the only thing I can imagine happening there, okay, is if you leave a bottle in the sun, with a little bit of moisture in it, what will happen is the sun will heat up that moisture and turn it into water vapor, which will fill the inside of the bottle. If you then put the cap on and prevent anything from going in or out, and you take the sunshine away, that water vapor will condense back into water, lowering the pressure inside the bottle, and so the atmospheric pressure outside will implode it.
Sorry, I just realized I was wrong there. It's actually the cold that's making it implode, isn't it?
Yes, that's right. So what's happening there is that if you have a little bit of moisture inside the bottle, the sun's energy will heat up that water and raise its temperature, which means that the molecules of water go into the vapor stage and they have more kinetic energy. They're moving faster. And if they move faster, when they hit the walls of the container, they're exerting higher pressure. That's what pressure is, the force of the molecules bumping into the walls of the container. If you then put the lid on so that no air can get back into the bottle and you cool it down, what you do is you condense that water vapor back into water, which takes up less space, okay? And so the water vapor condenses into water, takes up less space, leaving you with nothing in the bottle except a little bit of water in the corner. And so you have
when
a
it turns
higher
into
pressure
gas
outside.
or vapor, it's sort of it's moving
it
around
takes up
more
space. It literally takes up more space.
yeah. Okay, so right, cool. So that's interesting.
Right. Let me go back to the Joule-Thomson effect. I can see why Grimm wouldn't cite it. He wanted something to do with money. So I did the work for him, and I'm calling you out, Grimm. You've either misrepresented your position, you're stupid, or you're just deliberately trying to deceive. I'm now going to play a video of the Joule-Thomson effect, and let's see whether or not it's proving whether it's the pressure inside pushing something apart, or is it the vacuum pulling apart. That's the point we're trying to prove. And you cited the Joule-Thomson effect, and let's see whether it does what you say it does. So let me turn my screen up.
Dun, 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 dun.
So this is remember what the point we're trying to prove is. We're trying to prove, is it the pressure inside or is it the vacuum outside that's causing the thing to change its state? And this is what was cited by Grimm as the evidence to prove it's the inside pushing.
This looks like a cartoon. Is this a cartoon?
No, I'm saying, see, you just misrepresented what I said already.
No, that's exactly what you said, Grimm.
No, it's not. I said there's zero work being done.
Right. I asked, was it the inside pushing out?
The outside is not doing any work. The inside is not doing any work. There's no work.
I asked,
no
was
heat
inside
transferred.
Pushing out, or was it the outside sucking? And
you can't have a force of something that is nothing. Cannot apply a force.
It's called pressure.
Nothing. Pressure cannot exist without a force of material for it to be pressure.
You cited the Joule-Thomson effect to qualify it with the inside pushing out.
You misunderstand. Your limited ability to receive information and put it together into a mechanism is obvious.
Grimm, you've got one more chance to tell us.
Literally, I'm showing.
Grimm,
you're not understanding what you're looking at. I'll put it that way.
I know what I'm looking at because
you think there's pressure where a vacuum is.
Grimm,
like
tell
that's
me what
pressure. That's the vacuum and pressure are oxymorons. One is not the other.
Grimm,
one is the absence of the other.
You cited the Joule-Thomson effect.
Shadow. It's like saying a shadow has physical attributes, which you tried to do already too.
Grimm,
you don't seem to understand this fact.
Grimm, answer the question.
A shadow is just the absence of light. It's the absence of a thing. A vacuum is the absence of the pressure.
Grimv, you cited this as an authority.
It does not have physical attributes that way, dude. That's what you're not understanding.
Interrupting Grimv and answer the question. Tell us what the Joule-Thomson effect is before I play the video.
The fact that you think I did not just answer your question is quite alarming.
Answer the question. What is the Joule-Thomson effect?
The Joule-Thomson effect. I'll give you exactly what in thermodynamics, basically.
No, tell us what it is.
I'll show you right now. Is also known as the Joule-Kelvin effect. Right.
So you're looking it up.
So that's right. I'm reading it to you. The Joule-Thomson effect. Okay. It describes the temperature change of a real gas or liquid as differentiated from an ideal gas when it is forced through a valve or porous plug while kept insulated so that no heat is exchanged with the environment. This procedure is called throttling process or Joule-Thomson processes. At room temperature, all gases except hydrogen, helium, and neon cool upon expansion by the Joule-Thomson process. These three gases experience the same effect, but only at lower temperatures. The throttling process is commonly exploited in thermal machines such as generators, air conditioners, heat pumps, and liquefiers. It's very obvious. So zero work is being done. Okay.
No, hang on. So your position was, right, as far as I can tell, when I was asking, was it the balloon pushing on the inside or was it the vacuum sucking on the outside? You cited this. Okay.
It's the balloon pushing on the
inside. Let's listen to what this says in the context of that. You ready?
Any changes in the volume of a gas are accompanied by changes in its temperature. If we compress a gas and reduce its volume, its temperature increases. And conversely, if we decompress a gas, thus increasing its volume, its temperature decreases. This relationship is named the Joule-Thomson effect.
What's that got to do with the vacuum sucking or the pressure pushing?
Anthony, that's got absolutely nothing to do with the vacuum. That's got to do with expansion. That's got. Yeah, so why?
Yeah, that's his point, Paul.
I'm not.
I brought it up as far as
it's completely irrelevant.
I'm talking about there's no work being done when gas is being released into a vacuum. Right.
So you've
still no work being done when gas is being released into a vacuum because
did Brenda give you
the vacuum itself is not doing anything.
Grim, did Brenda give you that?
Anthony, the point is it still doesn't support your notion.
No, you're the one that's supposed to be supporting your notion. I'm asking for evidence that it's the balloon that pushes from the inside.
I've given you a mechanism by which pressure is caused. Pressure is caused by molecules hitting things, creating a force. You cannot create a force in a vacuum.
Of expansion discusses in the article is discussed in the article, which is gas or liquid at its one pressure flows into a region of lower pressure P2 without significant change in kinetic energy.
Right, but what's that got to do with the vacuum sucking or the insides of the balloon pushing?
Because the vacuum isn't sucking anything. Right.
But that's what we're trying to prove, and you cited this as proof, and it's not. It's got nothing to do with it.
Yes, it does.
How?
It's showing you the energy states of each thing. The vacuum is zero energy state, while the energy is relied in the mass of the particles in the pressure.
No,
Stupid.
Dude. No, dude. The Joule-Thomson effect is
look
that
at what I'm looking at. Tell me
the pressure increases, so does as the pressure decreases, the temperature increases. That's what it said.
Right, you don't understand what's going on here. Obviously, you just talk a lot, dude.
I've just given you your own evidence.
So much you confuse yourself. Well, obviously,
you've cited evidence, and it doesn't do what you said it did. So
yeah, it actually does. You just don't understand what it's implying there.
Right. So let me play it again then for the one of us that's not paying attention.
This experiment, it's showing you that you can take a piece of this experiment to understand what I'm talking about. This experiment doesn't demonstrate exactly that whole point because that's not the actual meaning of this entire experiment. But in this experiment, there are parts that you can use to understand the zero variability of the vacuum.
So what we can take from the Joule-Thomson effect has got a zero application that we're talking about.
So obviously, so what's your point? You think the vacuum is sucking something because you have the word vacuum and a vacuum cleaner,
and it's got nothing to do with it. Did you get this from Brenda? Brenda does this.
Say that to do this experiment in the first place, like this whole is it sucking or is it pushing thing, no matter what, you need two different atmospheres, like a vacuum and or like a container with a pressure in it, some pressure, and outside with some sort of different pressure is what you're talking about. And And like, no matter what, it needs both to have that reaction of exploding or imploding. Like, so you can't really say like it's. I mean, you can say, well, the force was caused by all of the air that we've put into this container. We're pressurizing the shit out of it. It's going to explode soon, sort of thing. Like, it's because you're whacking the air in there, and that is the cause of it, I guess.
Agreed. But if you do the same,
you do need two different atmospheres. You do need the two different pressurized atmospheres to have that effect at all.
You're pushing all the air into the balloon, and you know that that's what causes it to burst, and nobody disagrees there. It's the same conversely. If you suck all the air out of the environment that you're in, the balloon's still going to burst. But the point is,
right, Anthony, I'm going to put a stop to this. I've thought of an example. Right, I'm going to turn you all down and give you my example, whether you want it or not. So if you imagine, forget about vacuums and air, let's go into a submarine. Now, we all understand that if you fill a container with water and stick it on a scale, it has a weight. Well, that weight is its pressure. Now, if you had that submarine underneath all of that weight of the water, which is the pressure of the water, and it was only at atmospheric pressure, you would appreciate that if there was a hole put into that submarine, the water would rush inwards into the submarine. However, if you put lots and lots of air molecules to counteract the weight of that water that's pressing on the submarine, again, it will reach an equilibrium when you have enough pressure pumped into that submarine. Now, if we take it one step further and put more pressure into that container and then burst it, it would force outwards against the weight of the water. Now, that water, the weight of that water is in no way sucking the air out of the submarine. The pressure of the air inside the submarine is forcing against the weight of the water on the outside because it is of a higher pressure. There is a greater pressure differential. The pressure differential is what we are talking about.
Yes, I agree. In them circumstances, what you've just described is exactly right. However, when you do the exact opposite and you remove the submarine is the tanker. If you remove all the air inside the tanker, we saw it crumple. It needed an accelerant to do it, a dimple or a crushed, the stone dropping on the top of it, because they needed to, I don't know how that worked or why it worked, but they needed to do that to accelerate it because they couldn't do it without. But when we saw the plastic bottle on the inside, removing all the air on the outside of the plastic bottle meant that the inside blew its top. So the question is it the inside pushing up and blowing the top, or is it the outside pulling the top off? And I've asked for evidence.
There's nothing on the outside to pull.
So you say, prove it to be the case, because you can't prove it.
A vacuum has nothing. There is nothing in a vacuum.
It's the pressure that's pulling it.
There's no pressure in a vacuum because there's nothing there.
The negative pressure.
There is no negative pressure in a vacuum.
Nathan's way was good. That there's more pressure on the inside pushing out on the water.
Nathan's way was good when it's in this
trying to reverse it.
That would be the same for space, though. It would be the same up there.
No, it's the opposite. It's totally the opposite.
No, well, I'm sorry.
Yeah, you can make that comparison in the water, Anthony. You can suck all of the air out of the submarine, creating a vacuum inside the submarine, and then pop it. And the same principle would apply. It doesn't have to be at an equilibrium when you pop it. You could do it with a vacuum inside the submarine, and obviously the pressure of the water is going to force inside that container. And it's the adverse of when you pressurize it to force it outwards against the water. But as they keep telling you, when you are a vacuum, it is proven. There is nothing pressing against it. It has no force. It has no pressure.
So how do we prove it?
It's proven. It is demonstrated. You've had about 4 demonstrations played with balloons expanding their physical dimensions to fill the container. Literally, you can watch that balloon demonstrate this effect.
Well, you can't tell whether it's being sucked by the vacuum or pushed by the inside pressure.
You've literally got a compressor pump. You've got a compressor pump filling the balloon.
You need both. No matter what, you need both. And, that air is attracted to that vacuum. Like, it does want to get there.
Right.
All you've done by creating a vacuum on the outside.
Look like that initially is because of the pressure on the outside of the balloon keeping it from doing that. When you remove the pressure from the outside of the balloon, all the pressure from the inside of the balloon acts on on one side of the balloon instead of all sides of the balloon. Instead of the inside and the outside having pressure that keeps the balloon in its form, you have only inside pressure pushing on the balloon now. That's why, bro. It's pretty simple. I hope you understand
I
that.
fundamentally disagree, and nobody can prove
It doesn't matter
what's happening.
Anthony, you telling nobody can prove it all the time is not right.
Prove it then.
We've given you demonstrations for physically what happens.
But you haven't proved what's pushing.
I'm sorry, but explaining what happens from a physical point of view is proof.
No, it isn't. Explanation isn't proof. I want to see how we can prove that it's the balloon pushing on the inside or sucking from the outside. How do you prove that one or the other?
QED. It is demonstrated.
I understand it's been demonstrated, but you can't show which force is doing what. You can just show the effect of both of them.
Anthony, you keep on saying which force is doing what. There is no force on the outside.
I know, but you're saying it's the no.
Then
force.
why are you
disagreeing? Because it's a negative force,
That's
relatively speaking.
No,
you just said there's no
is not a force.
A negative.
He said relatively speaking, and I would give him that. Like, you're kind of right, man. You do need that negative force pulling.
Yes, it's a relative negative. It's a negative force relative to the force.
It's only opposite to the actual that you have pressure.
You're calling relative negativity, and it's not. It's a pressure. It's a pressure differential. It's not relative negativity. That's just a wrong term. It's a pressure differential.
Yes, but that is effectively, relatively speaking, relative to the balloon. It's a negative pressure.
But there's no need to redefine this term. There's no need. It's been defined. It is demonstrated. I don't understand why you want to call it negative relativity.
You can argue it into existence. Like, it's not you.
Nobody's proved.
It's done.
Everybody's explained.
Nobody's
proved whether it's the balloon pushing on the inside or the vacuum sucking on the outside.
You mean nobody proved it to you?
It's been explained, and it makes sense, but logic and reason isn't evidence. If we accept that as evidence, then that's you may as well just jump. You may as well be a baller because everything's based on logic and reason in the ball side.
Well, you may as well be, obviously, dummy.
I don't know. I don't know that. You need both sides, and the force inside is good.
Anthony,
I'm gonna have a small break. Sorry, I have a small break, and I'm gonna come back. I got a few topics I want to talk to you, Paul, if you've got some time.
Sure.
Okay, I'll be back soon.
Yep, thanks, Anthony. Things create forces.
Yes.
Okay. It requires something to create a force.
Yes.
In terms of the gas on the inside of the bottle, what's creating the force?
The gas on it. So the balloon's inside the bottle.
No. We're just talking about a bottle with some air inside. What's creating the force on the inside of the bottle?
I'm assuming the bottle's sealed.
Yeah.
And is it pressured or not pressured?
Well, it's under some pressure. What's creating the force?
Trying to trick you,
What's creating the force on the walls? What's creating the force on the walls of the bottle from the inside?
The pressure itself.
Yeah, but what? What is creating the force?
The volume of air.
Yeah, but what? Where does the force come from?
You blow it in with your mouth or put it in with a pump or whatever.
No. Physically, what is pushing on the sides of the bottle?
The pressure.
Yeah, but what? What is pushing on the walls?
The pressure.
Pressure is a measurement. What is pushing? If I want to move something,
the volume of air.
Push on. It's the molecules in the air that are bumping into the walls of the bottle that hit it, that put a force on the wall of the bottle. That's where the pressure comes from.
No,
it's literally it is literally the molecules of air bumping into the walls of the bottle that create the force. That is the pressure we measure.
So
that's
why is
what the pressure is. The volume of air inside the bottle remains constant.
No,
okay?
That's wrong.
I beg your pardon, but are you now telling me that the bottle's getting bigger?
As you increase the volume of air inside the bottle, the pressure goes up with it.
You can't increase the volume. It's in a container.
Same inside the bottle.
Can't increase the volume.
The container is
no, it doesn't. So you're saying the pressure remains the same with the volume?
No, Anthony, the bottle is the same size. Its volume does not change.
Right. So what then makes the pressure change?
If you put more air in there, there are more molecules. There are more molecules pushing on the wall of the bottle.
You put more air in there. You've just said
That's right.
Right.
That's
so
correct.
As the volume of air increases, the pressure increases with it. Yes.
No, we need to define what you mean by volume. The volume is the amount of space inside the bottle.
No.
You're talking about putting more. You're talking about putting more mass of air inside the bottle.
Yes.
That's the terminology we use.
Yeah, okay, we'll go with
is 1 litre volume.
Okay. Do you understand what I mean?
Coke bottle.
The volume of the bottle is a fixed size. It doesn't change. That's right. So when I put a greater mass of air, when I put more air, let's not talk about volume of air. Let's talk about we put more air inside the bottle. You agree?
The pressure will then go up.
Because there are more molecules of air banging into the side of the bottle. Yes.
Because you're just putting more air into it.
That's right. And so we have more molecules of air to bang into the side of the bottle.
No, you just have more air.
I beg your pardon. But if I put more air in the bottle, there are more molecules of air inside the bottle.
No, there's just more air.
He's taking a piss on you, dude. This is baloney.
No,
you know he knows what you're saying. That's not. No one doesn't know what you're trying to say. I can't believe anyone who couldn't understand that simple concept.
You just put in more as the air goes in. The more air goes in, the pressure goes up. It's that simple.
The reason why the pressure goes up is because there are more molecules of air to bump into the side of the bottle.
No, it's not. It's because there's more quantity of air going into a confined space.
And therefore, there are more molecules to bump into the side of the bottle.
Fine. If you want molecules to be involved, fine. Go on. You can have your molecules.
That's what air is made from.
Molecules, but it's to do with the quantity.
You wouldn't have air pressure, silly.
Oh my God, Anthony, you just said it's to do with the quantity. What have I been saying all along? I said that we have more molecules bumping into the side of the bottle. That's what a greater quantity means.
Silly.
If you want to talk about it in molecules, fine. Do we both agree that it's to do with the quantity of air in a confined space going up?
Yes.
Fine.
I don't know
because there are more molecules bumping into the side of the bottle.
Well, you can have your molecules. I'm rejecting the molecules bollocks rubbish because that's
so air's not made of molecules.
Said, can we both agree?
Let's go with the point where we both agree. As the air goes in, the more air goes in, it's a confined space. The pressure goes up. We both agree at this point. You can have your molecules.
Why does the pressure go up?
Doesn't matter if you
because you're increasing the volume of air inside the space that you're in. You're keeping the space the same.
Why is the pressure going up? What is the physical fundamental property?
It's the same as inside an internal combustion engine.
Molecules.
The piston goes up and
the number of molecules and interactions. That's the answer.
It's the same it's the same as inside the engine. When the piston goes up, what you're doing is reducing the size of the bottle so it creates a compression. But you're not changing more. You're not making more molecules.
Yeah, but you're reducing
they're going faster.
No, but you're reducing the size of it.
No. All you're doing is reducing the size of the container.
And therefore, there are more molecules hitting per square centimetre.
That's right.
Well, you can have the molecules. I'm just going with
it. The same, buddy.
Anthony, before the piston goes up, there is a bigger surface area for the molecules to hit. You've got the same number of molecules.
I'm not accepting your molecules.
Anthony, listen.
We both agree
you have the same number of molecules hitting a smaller surface area when the piston is up, and therefore there are more molecules per square centimetre.
I'm not having molecules.
So air is not made of molecules now?
It is made of molecules, but
then why are you rejecting
you going through all of that? Because that made good sense, and I appreciate that very much. Much less space for the same amount of molecules equals also another way to change the variable on the pressure, and we don't argue that.
Yeah, but you think the Joule-Thomson effect was something to do with this discussion? So I mean,
it does.
The fact that you're satisfied doesn't really make me feel as though I'm not.
The vacuum is zero. It's at zero potential.
No, it's got a negative pressure relative to
it has no work there. You're not seeing the math on it that I'm seeing. You're not.
No, I see.
Not really internalizing the work like I do. I guess you're just seeing the glance thing, and you're not understanding what all of those things imply.
Rubbish.
Right. In that Joule-Thomson effect, it does imply that there is a zero potential base for your so-called.
In the Joule-Thomson effect, it talks about the
so zero potential, no energy.
The Joule-Thomson effect is the
no work being done, no math.
Goes up.
hello, you're not realizing what I'm trying to say.
It's completely
trying
irrelevant.
to use one aspect to try to use it out of context when I'm trying to do the same thing.
You cited it to prove what we're talking about, and it was nothing to do with it. Absolutely.
I just explained that, you knucklehead.
Right, but you cited it as an authority.
My goodness. And well, it is. Actually.
No, it isn't. It's an authority.
The experiment is verified and there is no work being done, meaning there's no potential on that end of the vacuum, which is all I was trying to use from the experiment. Like
it was completely irrelevant.
Yeah. So it's obvious. And then all of these obvious explanations for pressure that you don't seem to understand.
No, I understand.
The vacuum is just the lack of these particulates bouncing around. It doesn't mean that there's a suction going on.
All right.
So get real, man.
Yeah, okay. Well, do you know what? I can see why you all believe everything that you're told.
Oh, sure. Do I? Really? That's why I'm a plasma cosmologist. How much sense do you make? I don't believe in gravitationally based theories.
Are we on the same planet?
How much sense do you make?
And it's right now. It's incredible that adults
right now, Anthony.
The stuff that we're told these days, literally incredible.
High five, Anthony.
No evidence. Can't prove your assertion.
It's all right, man. Handshake. I just believe everything I'm saying. I'm an anti-vaxxer. I believe everything I'm told, huh? I'm an anti-vaxxer, dude. All right, for one. I don't vote for either one of the two Jesuits that were provided to me. But I believe everything I'm told, right, buddy?
Could you stop screen sharing, Grim, just because I've had to go to photographs just to stop people getting epilepsy?
But I mean, you can read further and you can find out more about the units of pressure and talk about that too.
Or we could just make it up, make it sound logical and reasonable, and let people believe it.
No, that's your thing. I don't like to do that.
No, but that's exactly what's happening in this conversation.
No, that's what you do. That's why we get theories from you about we can see the shadow of the moon pass through the brilliance of the sun during an eclipse to give us what we think is the face of the moon in front of the sun. That was you, right?
What the hell are you talking about?
That is the silliest stuff I've ever heard in my life.
If you're meant to be quoting me there, you've made a hash of it.
Shadow of the moon through the sun. You're telling us the moon is on the other side of the sun during an eclipse.
That's what the evidence tells me, yes.
The evidence doesn't tell you that.
Well,
it's like, well, that's what the Lord tells me. So yes.
No, not the Lord. I don't do religion. I do evidence. And this is why I'm asking how can you prove that the moon pushes rather than the vacuum?
So we have approximately 1 hour, left on this live broadcast. So if you've not done so already, be sure to share the show on social media. Smash that share button as it increases the audience, and that in turn increases the likelihood of a more diverse panel. If you are new to this channel, be sure to subscribe and hit the bell notification icon to keep up to date with the Flat Earth debate. If you would like to support this channel or you're enjoying what you're watching, toss me a buck or two in this super chat that runs alongside the show while it is live. And most importantly, if you would like to join the panel to express your views on the shape of the Earth, simply click on the link in the info box below this video. Be sure to mute the page you are currently listening to me on before you click that link. There are a couple of rules in the Hangout. Number 1, please do not swear. If you do, you will be ejected. If you are, please don't try to rejoin the show using sock accounts. You will be warmly welcome back on the next stream. As I say, if you've not done so already, please share the show. And if you've not subscribed, hit that subscribe button and the bell notification icon to keep up to date with the Flat Earth debate.
I'm even granting you extra privilege by giving you the second light bulb. You realize that, right?
Dummy? Can you stop sharing, Grim? I just want to come off the photos on the live stream.
Oh, sorry.
Ah, brilliant. There we go.
My bad.
On a different note, Paul, when you came in and you showed the little stick thing, I don't know what it was. It was like a dog or a cat thing. And you said that image was taken in the dark. And I thought, no way. I actually learned something because I went out and I looked at long exposure photography taken at nighttime. And I agree with you. It is in color.
Yeah. The light from the moon has exactly the same properties as the light from the sun.
Do you not?
It's just a lower intensity. It's a much, much lower intensity. And so you need a long, long exposure.
Do you agree or disagree that the light from the moon is polarized?
Light can be polarized. Light is polarized when it gets reflected off of anything to a certain degree, yes.
Do you therefore agree that the sunlight is not polarized?
No, that's not correct.
Boy, Paul is on
it. It depends.
He's got all my answers. I like you, Paul. All right, high five, brother.
I'm a physicist.
Oh, well, no wonder we get along. It's only the knuckleheads that argue with me and tell me I'm wrong about everything.
Yeah.
What'd you do, Paul? That's interesting. I didn't know you were a physicist.
Back to the moon.
When light gets reflected off of anything, it gets polarized. The shallower the angle of reflection, the more it's polarized, and that's why Polaroid sunglasses block reflected light from surfaces. That's why they're so good.
I've always wondered how they work, but so the light from the sun is not polarized, or it is?
It depends on what you mean.
Well,
if you look at it directly from the sun, like without it going through anything, then no, it's not polarized. But as soon as you make it go through something or reflect off anything, then to a certain degree, it is polarized.
Welcome to the Rayleigh effect. Basically, why is the sky blue issue? You know?
Rayleigh scattering. Yep. So then, by definition, if you apply the Rayleigh scattering to the sunlight, by definition, it should be polarized because it's going through the atmosphere, right?
Partially. You're not
so basically, it starts out not polarized.
Coherent light going on.
Been joined by Arave. How you doing?
Hey, I'm good. How are you?
Are you driving?
Very pleased to have you here.
Yeah. How'd you know?
It just sounds.
We can hear your car.
Yeah.
Oh.
You're not normally driving when you're in here, are you?
Most of the time, yeah.
All right. Okay.
On my way to work.
It just seems more prominent today than ever before, but okay, that's fine.
Check engine lights on. Got to get this thing serviced.
Ignore all of them. You sound
like
fine. Everything's great. Everything's fine. Your sound is fine. Just ignore the other guests. Just worry about what I tell you in that regard.
But it sounds like the light starts out not polarized, and then it has to hit something to be polarized. So in a way, it's kind of like saying, so sunlight is not polarized, right? At least starting out.
Yeah, that's right. What's the point?
Then it comes through the atmosphere, though, right?
Yeah.
Does that not then polarize it?
Partially.
Is it not black and white? It either is or it isn't.
No, there are different degrees of polarization.
Okay. What about, on a different topic, what about...
What were we talking about?
Well, I'm just going to... If Paul's a physicist, this is really interesting, because the one thing that I wanted to catch up with a physicist about is the properties of metals in terms, or properties of substances, which can be ranked in terms of their overall general strength. Like, so in contrast, you could say like aluminium is not a strong metal compared to, say, steel that is a strong metal. And then you can say concrete is strong in contrast to, say, carbon, which is not strong, right?
Yeah, I mean, there are different measurements of strength. You've got tensile strength, you've got shear strength.
Yeah, I was going to say, for its weight, like strength per mass. Right?
So basically, aluminium is not generally considered to be a strong metal. It is light, but it's not a strong metal compared to steel.
Would it not be stronger than, other alloys or metals?
It's like any metal, Anthony. You can increase the strength or decrease the strength by doing various things to it. If you work harden steel, it gets stronger. Yeah, you can make aluminium relatively strong.
Comparable to steel, though, you can't compare it to. You can't make it comparable to steel, right?
Well, you can compare it to anything.
No, comparable. Make it comparable to steel.
Right, it's always comparable. But
can you make aluminium as strong as steel? Yes or no?
Not for its same
I
size.
guess what Anthony's trying to ask that different materials have a different Young's modulus.
And what about carbon over concrete? Carbon's not strong, whereas concrete is strong. Can we agree on that?
It depends. It depends what application you're talking about.
How do you form
Well, it sounds like, it sounds like you need a strong structural steel to keep the pressure from the ISS from being sucked into the vacuum of space. I mean, one hole, one rip in the integrity of the structure, and all the gas would come pumping out.
14 pounds of pressure?
And you've never seen anything but an enclosed system be next to a vacuum. So if we're not covered by a dome, why isn't the air from Earth sucked out into the vacuum of space? Why is this vacuum in space so magical that it doesn't suck the air out of the Earth or out of the ISS?
How's a Pepsi can hold 55 pounds of pressure?
You need to have a good structure around the vacuum, yes.
It's a Pepsi can that can do this. 55 pounds.
For a relatively small amount of
14
pressure.
pounds? I think, I can't remember. Do you remember what that PSI is?
For a carbonated drink?
30.
No,
30.
for the pressure in the ISS.
14 psi.
Yeah.
Yeah.
Which is basically 1 atmosphere.
But is that a good example? Because freeze the can or change the temperature of the can and it bursts. And isn't the ISS going through similar temperature changes going in and out of the atmosphere? I mean, what engineering feat is able to keep the ISS from falling apart?
I'm sorry, but freezing a liquid like water, and when water freezes, it expands, is completely different from cooling an air inside a container. Not even comparable.
Will apply with the expansion of the gases or whatever? I mean, does the same principle basically apply with the air? Just a different medium?
No.
I run out of voice. Like I get hoarse talking to these guys, trying to tell them no.
Could I just go back to what I was getting at with regards to the steel and the aluminium?
Yeah, sure.
I'm just wondering what your position is with regards to 9/11 and the 3 buildings collapsed, but only 2 planes hit it. And assuming that planes could do what they tell us they did, how does 2 planes cause 3 buildings to collapse?
I don't know.
What is your position? Do you believe the official narrative, or do you think that something else happened?
I have no problem believing what they've told us there.
Oh, right, okay.
And what has that got to do with what has that got to do with the shape of the Earth?
Well, not to do with the shape of the Earth. I was just wondering about what your position.
Well, then let's not talk about it. It's irrelevant.
I was just wondering what your position was as a physicist.
Huh? I've got no problem.
Let me ask you a question, Anthony. Do you prefer leprechauns or unicorns?
Well, before we descend into fast, we've been joined by Physics Warrior. Very pleased to have you here, Physics Warrior.
Hey, Nathan. Hey, guys.
At least we have some common ground, Anthony. We both love unicorns.
Yeah, unicorns kick ass.
Well, it is kind of insane that molten metal was found at the site, as if somebody used thermite to melt the pillars down. I mean, buildings with steel girders have burned for hours and still stood, yet all of a sudden the Twin Towers fall with a similar fire, quote unquote. At best, the planes hit the towers, yes, and then somebody had a finger on the detonation button for the thermite explosives in the basement, which was the second part of what made the building collapse, with the molten metal present at the site for weeks. And then all of the metal, which was technically evidence of a crime scene, was shipped off somewhere and destroyed. It's all very fishy.
Sorry, I thought you were going to bring this onto the shape of the Earth, Ara. If I've got to agree with Paul, what's this got to do with the shape of the Earth?
Well, China's on the side of it, and that's where they ship the metal.
Hey, I want to go back on the ISS structure.
Excellent, excellent.
I mean, here's the thing. I mean, yesterday you guys are saying it goes like 17 to 20,000 miles per hour. So they say. But glass, solar panels, how is it able to stand the tensile strength of that speed and also the pressure?
Tensile strength at that speed is a nonsense statement. Tensile strength is not related to speed.
Okay, so then
speed's got absolutely nothing to do with tensile strength.
But to be fair, it's only as nothing. To be fair, it's only as useless as citing the Joule-Thomson effect for proving whether the balloon bursts on the inside or not.
You know,
but again, tensile strength of the glass.
Engagements.
What about able to withstand all that?
All that speed. Speed's got nothing to do with tensile strength.
Yeah, you can have a ball of water with just water surface tension going that fast and that.
So that means if I throw your phone down with speed, it won't. It has nothing to do with tensile strength.
You can actually get it spinning, spinning. Ball.
It's not the speed; it's the stopping at the end that breaks the phone.
Yeah.
Okay, but you're not answering my question. So the strength of the glass itself.
Wow,
I am. What about the strength of the glass?
You mean the glass itself is actually can work in those conditions? I mean, right now we carry glass, we break glass all over the place. So I'm trying to find out why is it the glass up there is perfect.
Have you ever seen a bell jar vacuum chamber?
No, but I've seen glass break.
Have you seen a bell jar vacuum chamber?
I've seen glass break naturally.
Do you know what a bell jar vacuum chamber is?
No.
It's a glass jar.
We have to have at least high school graduates over here, guys.
I know. It's a glass jar, and they create a vacuum on the inside, and blow me down, it doesn't break.
So?
Okay.
Glass can withstand vacuum, no problem.
Blow him down right now. It doesn't break.
Does it mean tell me if I were to bring it down to like the deepest ocean, glass won't crack?
Yeah, down to 0, and it won't. If it's not.
That's right.
Designed for that, yes.
I wouldn't believe that.
How do you think they
can temper glass? You know that you temper it.
What do you think the lenses? What do you think the lenses are made out of that they photographed at the bottom of the Marianas Trench with?
Glass.
Paul, you know what do we get when lightning strikes the beach? Glass.
Paul.
Yeah.
Talk to me about the Curie temperature.
Yeah, the Curie temperature is that temperature at which a metal will no longer hold a permanent magnetism.
Great.
However, Anthony, it has absolutely nothing to do with the ability of that metal to then generate a magnetic field.
Great. Have you got any evidence to show where iron in molten or solid state when it's at 7,000 degrees Celsius is capable or can either create a magnetic force or become conductive? Either of them will do.
I beg your pardon, that iron, when it's molten, can become conductive. Metals, by their very structure, are conductive.
Right. So
that doesn't change. That doesn't change whether they're molten or not.
Right.
It's more conductive as a plasma, actually.
Hold on, Grim. Hold on, Grim and Anthony. Hold on. Just before you.
I'm good.
Hold on. If you want to rephrase it again, Anthony, that's great. Just rephrase it again. But I just want to say hello to Tony before you do. How you doing, Tony?
Hey. Thanks for letting me on.
You're really quiet.
Hey.
So, good to have you here, Tony. Thanks for being here.
Hey, you hear me?
Yeah, we can now. I've turned you right up.
Okay.
Thanks for being here.
Keep going.
Sorry, guys. You carry on, Anthony. If you want to rephrase your question again, great.
Okay, so I'm sharing my screen now, so you should see the Curie temperature. When we look at the Curie temperature, as you correctly identify, when it gets to a certain temperature, it will lose its magnetism, its ability to hold a magnetic charge.
It's no longer ferromagnetic; it's paramagnetic.
And it's what the temperature is about 700 degrees Celsius, right?
That depends on the pressure as well.
Sure, but at normal atmospheric conditions, the temperature, the Curie temperature is around about 700 degrees.
So
the temperature of the core of the Earth, cited by your lot to be 7,000 degrees, roughly.
Yeah, there's no problem with that. But I've already stated that the Curie. But the Curie temperature has absolutely no relevance whatsoever with the ability of that material to create a magnetic field.
I know, I heard what you said, and I'm about to discuss it, so let me carry on. Do we agree that on the model that you guys believe it's A, solid, and B, iron?
Some of it's solid, some of it's liquid. It's not all solid.
The inner core. Let's go with the inner core, for example. It says
the inner core, yes.
Solid, yeah. Do we agree that the temperature that they cite is 7,000 degrees Celsius? Sorry, 7,000 degrees Kelvin, and then nearly 10,000 Celsius.
Approximately.
Okay. So given that iron melts at what, 18? Well, it melts at about. Let me get the details. melting point of iron. 1500 degrees C for melting.
Yeah, I was going to say, I thought it was like
atmospheric pressure.
That's right. That's right. And then the boiling point is 2800.
At atmospheric pressure.
At atmospheric pressure, you're quite right. So, do we agree that the Curie point, the melting point, and the boiling point have all been massively exceeded by the claim of the temperature of the core being like nearly 10,000 Celsius?
No, we do not, because the boiling point and the melting point vary vastly with temperature, with our pressure. Sorry.
Okay, so then we look into the phase diagram of iron, right? When we pull up the phase diagram of iron, click on images. That one will do because it's clean. So there we go. So let me zoom out a little bit. So at 1 bar, which is generally us, the point where it boils from a liquid to a vapor is basically 2800, which was, I think, where we got to on that. Oh, I've got rid of it now. But so what you're saying is, as the pressure goes up, then what?
The boiling point goes up, and you can see the steepness of that curve.
So is your position that the core is solid because the pressure is high enough to keep it as a solid? Is that what you're saying?
Absolutely.
Great. Have you got any evidence to prove what the pressure of the Earth is to support your assertion?
I've got reasoning to suggest that it is very high.
He doesn't. Nobody's
You can't use reasoning. That's too reasonable.
Alex gave reasoning, and he showed that it was based on conjecture. I'm asking for, do you have any evidence?
Anthony, we've measured the pressure at the bottom of the oceans to be well over 1,000 bar. That's 1,000. Okay, what's that got to do with it? Do you know what a chain of reasoning is, Anthony?
Yeah, it's called conjecture.
No, it's not.
Yeah, it is. Just like what you were talking about.
A chain of reasoning is where we use things that are well understood to explain other things. The pressure at the bottom of the ocean is measurably well over 1,000 bar. Okay. Now, what if I was to replace the water in the ocean with something that's on average 5 times denser? Would you expect that pressure to go up or down?
Well, hang on. In the ocean's irrelevant. We're talking about inside the Earth.
No.
Yeah, it's not even making gravity either.
Follow me here, Anthony.
No, we're not following through. Chain of reasoning is not evidence. The point is...
I'm sorry, Anthony, but the pressure at the bottom of the oceans is over 1,000 bar.
Yeah,
If I now replace that ocean with rock, in other words, now I'm not at the bottom of the ocean. I'm the same distance below something that's 5 times heavier.
Sure, but what we're talking
about, the pressure will be higher. Why not?
Talking about the pressure inside the Earth, not the pressure at the bottom of the ocean.
That's right.
Because there's a lot of water.
The pressure will be higher.
Right.
The pressure will be higher at the same depth below something that is 5 times heavier.
All right. Well, let me put it to you in context.
Does that make sense, Anthony? Do we agree?
No. It makes sense.
Anthony.
No. That is not. It makes sense.
Anthony, do we agree that the pressure will be higher with rock on top rather than water?
Yeah, sure, but it's irrelevant.
Okay. No, it's not irrelevant. No, Anthony, because now what I do is I put even more rock on top. In other words, I go deeper, putting more rock. The pressure is going to get higher.
Fine, but it's irrelevant to the point.
And we go deeper and the pressure gets higher.
Right? And there's no place for the vapor to go.
Okay.
I get what you're saying, but it's irrelevant to the point. I'm asking about the pressure inside the Earth, not at the bottom of the ocean.
That's what I'm saying.
No, you're not.
Anthony, the pressure at the bottom of the ocean, 1,000 bar.
Yeah.
If I go the same distance, listen to me. If I go the same distance below rock, which is 5 times heavier, I would expect the pressure to be higher because I have more weight on top of me.
But you can't prove it, can you?
So he's saying with his conjecture, with that pressure with water, assuming that the Earth is just solid rock, there should be even more pressure at the center of the planet, leading to a molten core. But like you say, that is reasoning from a chain that assumes, I guess, a solid Earth. Who knows, the Earth might be bobbing on foundations and have a totally different construction, which is what makes these assumptions dangerous. Sometimes the premise can be false.
Absolutely.
You know,
and I'm about to demonstrate how it is false. I'm about to demonstrate
different construction.
I'm about to demonstrate exactly how it's false. So I'm going to assert to you with evidence that the pressure of the Earth is nothing like what you're trying to tell me or persuade me it is based on logical reasoning. And we can use volcanoes to do it. If there was loads of pressure of the Earth, the volcanoes will be erupting all the time.
I'm sorry, but the magma from volcanoes comes from near the surface, not from down near the core.
Yes, the mantle.
If the pressure of the Earth was as high as you're saying, volcanoes will be...
I beg your pardon, Anthony, but the pressure of the lava that comes out of a volcano is near the surface.
Paul, do you know what the deepest hole?
It is nowhere near the core.
Doesn't matter. If the pressure inside the Earth...
I'm sorry, Anthony, but pressure decreases as you get towards the surface.
It's not true. I can prove that that's not true.
I beg your pardon.
I can prove that's not true.
I'm sorry, but
I can prove that's not true.
But at least let him try. At least, Paul, at least let him try.
I can prove that that's not true, Paul.
Go ahead. Try.
Go ahead.
Do you know what the deepest drilling hole that we've ever drilled in the Earth is?
Yes, the Kola Deep.
Do you know how deep it went?
About 12 kilometres.
Right, and do you know what the results were of the rock? What the density of rock? What when they were digging this hole? Do you know what the result of the density of the rock was?
I have no idea.
No, because when they were digging, they found some unexpected results that they weren't expecting to find. Let me just try and find. I think it's on this one. Give me a chance to find it. The density of the rock decreased once they got to a certain depth.
And that's got nothing to do with the pressure.
Holy
well,
moly.
it does, because you're arguing that the density of the rock and the weight above it is pushing down on it.
I said nothing about density.
I
said the weight of the rock above. I didn't
Density is the glitch.
say anything about density.
Yeah, but different rocks are formed differently. I mean,
that's density.
That's right.
You just say,
yeah, but the whole point is that the pressure gets, as you go deeper. You were saying that the pressure gets more and more and more.
That's
relatively, that's still at the surface, though. Like, relatively, that's still at the surface.
Rock would also increase.
Yeah, it could be water under there.
No.
Yeah, of course it would. You can't get less dense rock if the pressure's going up and up and up because of the weight above it.
Of course you can.
How?
Couldn't you? Because different rocks are formed differently.
Yeah, but that's right.
But as the rocks get heavier and heavier,
full of crystalline, and they're very dense, and they're
different rocks are made of different materials.
Yeah, but hang on, we're only applying your rules of logical reasoning here.
No, you're not.
Yeah, we are.
No, you're not applying logical reasoning at all.
The rocks got less dense as they got deeper.
So?
Therefore, there should be less pressure.
Things getting heavier and more pressure on top because it should be getting more.
No, you're thinking that all rocks in the same pressure form the same densities. And they don't.
I'm saying that the density of rock...
you must be, because you're trying to apply that rule right now.
I'm saying that the density of the rock decreased as they got deeper, not increased.
To argue with stupid people.
Sure, okay. Well, all right, let's move on. So the deepest mine that they dug, the deepest hole that they dug got down to 8 miles. So what you're saying to me is that we have to apply logic and reason, essentially, to conclude the rest of the stuff. Is that what you're saying? Because at the moment, I'm asking you for evidence to prove that the pressure is high enough to keep the iron at a solid, and you're not giving any evidence, you're just giving conjecture, and I'm not accepting conjecture. So unless
8 miles is still the surface, it's still like, that's not even like
to a guy who wants you to prove internal equinox.
Unless you can prove that the pressure goes up inside the core or inside the earth, then you can't assert that the iron can still be in a solid state. In any event, I'll give way. Let's just pretend that it does. You know, we'll just apply the conjecture because that seems to be the standard of evidence.
Anthony's pretending and ignoring.
Anthony, does the pressure of the ocean get higher as you go deeper?
I'm not talking about the ocean, Paul. I'm talking about the earth.
I don't care. It's the same.
It's an irrelevant point. You may as well cite the Joule-Thomson effect, Paul. It's completely irrelevant.
It's the same principle with the rock.
No, it's not at all.
It is, because you've got more material on top of you. The pressure will be greater.
All right. I disagree with you, but I'll give you the point so we can move forward. Have you got any evidence to prove that iron in its molten state, be it liquid, solid or otherwise, at the temperature it's at, as by your model, is either magnetic or conductive? Because it needs to be both for it to do what they say it does. So, as a physicist,
Can you prove that iron in its molten state at that temperature is, because it's basically, it becomes supercritical at that point. Is it conductive, Paul, or is it able to be magnetic? And if you've got evidence, I'd like to see either. You've got two chances there.
I beg your pardon, but you're the one asserting that it's not magnetic. You prove that it's not magnetic.
Yeah.
No,
you prove
you have the burden of proof, Anthony.
No. Let's go.
He already showed it with that law that he cited that said that metals at high temperatures and high pressures basically lose their magnetism. So this molten iron would not be magnetic. So what is the source of the Earth's magnetism at that point? If this is defying some sort of Thomas whatever law, there are inconsistencies here.
Let's go back to the beginning. Stop, guys. Let's go back to the beginning. The assertion of the spherical Earth model is that the inner core is both solid and iron. Okay, it doesn't say iron on this illustration, but it is. It's iron. That's what they say it is. There's a little bit of nickel in it, but essentially it's iron. Okay. I showed that once the Curie temperature is met, it says that it loses its magnetism. It says here
it loses its ability to hold permanent magnetism.
Right. Right. This is the bit that you're not getting.
We've already gone through this a little bit before, though.
To be replaced by induced magnetism. Okay. So it loses its permanent magnetic properties. That means it's not magnetic. But
that does not mean it's not magnetic. It means that it won't hold a magnetism.
Agreed. Yeah. To be replaced.
Let's not rule out the idea that we're sitting in
I agree with that.
Electric field already. The Earth is, and that they're magnet. It's a theory about this magnetic field being generated by the Earth's core spinning, but it could be the very opposite. It could be the magnetic field generated by the induction of magnetic fields moving through plasma. You know what I'm trying to say?
I hear you.
Yeah, there's a whole nother aspect that's being ignored, and it could be the whole aspect. It's the drive of the planet, the EM field that we're sitting in, the sun's electromagnetic field. That we're sitting in.
Sure. Well, I'm going to go back to this point. So the distraction.
Right. And then NASA just discovered the Alfvén wave. See, Hannes Alfvén is the father of plasma cosmology. NASA just discovered and announced their discovery of the Alfvén wave, and that is the kinetic wave in plasma. And this is the first time they were able to fly these spacecraft so close together to pick up these sort of readings to understand what they're dealing with out there. That there's an actual kinetic wave in the plasma, showing that this plasma field outside in the heliosphere here has capacitance, which it wasn't thought that it would. It actually held a charge, but it does hold a charge, and it's pretty interesting, that
Graham, you have that link. Can you put it in the back chat?
Well, I know Paul knows that EM fields are 1,000 billion times stronger than their the strength of their gravity-based theories, their gravity alone, right?
So I agree with that. Can we go back on topic now?
we kind of are on topic, aren't we?
Kind of was.
Yeah, but
put the link
because this is the idea that's explaining why it doesn't matter how hot the core of the Earth is for the magnetism to exist, because there's another mechanism for the magnetism to exist. Is what I'm proposing here.
But can you prove that that's the case?
I think it's directly on topic, like smack dab hammer on the head of the topic.
Can I have a few minutes to talk here, please? Can I have a few minutes to talk here, please? Okay.
Go ahead, Paul.
No, I really need to talk here now. Okay, you keep referring to the solid center of the Earth, the solid core. That's not the part of the core that's implicated in the generation of the magnetic field. It's the liquid part of the core, because the liquid part of the core has convection currents in it.
All
right, those convection currents. Okay, do you understand what the structure, the atomic structure of metals is, Anthony?
It's irrelevant to the point. The point that
it is not irrelevant.
What you need to demonstrate.
No, it is not irrelevant.
The only thing you need to demonstrate, Paul, and I've been very clear, is that
you need to listen to me, Anthony. I asked you.
No.
Do you know, Anthony? I asked you a question. Do you understand what the nature of the bonding in metals is?
I asked for evidence that shows.
No, Anthony, I've asked you a question. Do you? It's a yes or no.
I don't need to.
Do you understand or don't you understand what the nature of the bonding in metals is?
Why haven't you answered my first question? I asked you.
No, because I asked you a question first.
No, I asked you first.
No, Anthony, I am talking here. All right.
Yeah, I know you're talking.
I'll give it to you here, right? The bonding in metals is such that a metal has non-localized electrons in it. These electrons are able to freely move throughout the metal, and that's why metals are such good conductors of electricity.
Yeah,
okay?
I know this.
Now, if we have a convection current of metals, all right, so you can imagine these metals swirling around, rising and then falling and rising and falling because the heat generated in the Earth's core, okay? Free electrons, when they're moving, constitute an electric current.
Yes.
Okay.
Now, which ones do that, Paul?
Let me finish, please.
Which ones do it, Paul?
And let me finish. An electric current, when you generate an electric current, you also generate a magnetic field.
I agree. However,
and that is the principle where the magnetic field of the Earth arises.
Have you got any evidence to prove that's true?
The moving current, right? The moving core, the moving metal it constitutes an electric current, and that generates a magnetic field.
I agree. But, and there's a big but, it doesn't do it to iron. It'll do it to sodium, and I'm showing on screen now, this is an example of sodium doing exactly what you're saying.
All metals, Anthony, have the same metallic bonding structure.
Prove that iron will do it.
Metals have the same... I beg your pardon, Anthony.
Prove it.
Can I just ask?
It's already been proven.
I got a question.
Sorry, it has already been proven. I'm sorry, Anthony.
Well, there's a bit of discord, a bit of back and forth. I'm going to do my links as there is approximately 1 hour left on this live stream. So if you are new to this channel, or you have not done so already, be sure to subscribe and hit the bell notification icon to keep up to date with the Flat Earth debate. If you would like to support this channel, there is a super chat that runs alongside the show while it is live. And if you would like to join the panel to express your views on the shape of the Earth, simply click on the link in the info box below this video. Be sure to mute the page you are currently watching before you click on that link to join the show and express your views. There are a couple of rules. Number 1, please do not swear. If you do, you will be ejected. And number 2, if you are ejected, please do not try to rejoin the show using sock accounts. You will be warmly welcome back on the next stream. If you have not done so already, please share the show on social media. And one last time, if you are new to the channel, or you're one of the 50% of the people watching this who have not subscribed, hit that subscribe button and the bell notification icon to keep up to date with the Flat Earth debate.
Over and over.
Prove iron does it. There is no evidence to prove that it does it.
Above QE. Above the QE level.
Wow.
Well, that's the thing, right? So, like, you get down to a level in the Earth where it goes solid for a fair while, I imagine. And then we start getting to this hot section of it due to... well, see, that would have just happened over a long time, I imagine. But... In this part, it's kind of weird because this theory would basically be like some sort of like it would look hollow more or less, but it's like or kind of like solids returning to gases, but still having the gravitational pull to be massively heavy and dense, like it would be dense liquids,
like silly putty.
What you just said there, dude, is it? Iron.
It's something unimaginable, which is what's weird, which is why we couldn't really answer this topic before.
Paul's assertion is that all magnetic metals do this. They don't. There is only evidence for sodium.
No, your assertion is that they don't.
No. My assertion is it's limited to sodium, Paul.
But your assertion is that they don't.
No, it isn't, Paul. My assertion is that it only does it to sodium because that's all that can be proved.
That they don't.
Still have and you would still have solid shells.
Paul,
you would still have solid shelves that could produce magnetism as well. Though.
Paul, my assertion is that the only evidence that exists is relating to sodium. You can't cross-apply it to everything unless you can prove it's true. And there is no evidence to prove that iron does today.
This video is the only evidence there is? Is that what you're saying? For real?
No. The only evidence that's been produced is that sodium will do it. But Paul's jumping the gap between sodium to all metals that are of a similar nature. No.
Okay, ask the question again. Restate the question again just so I can write this down and then go look it up. What's your question again?
Write this down. Sodium, when heated so that it melts and spun, will create an electrical current and a magnetic field by virtue of it being sodium. However, iron won't. And I know that because there is no evidence to prove it's true.
No, that's not the way you assert things, Anthony. You do not say, no, you do not say that it won't because there's no evidence.
Prove it.
Is false. That is false reasoning. That
No,
is
it isn't, Paul. It's called deception.
I beg your pardon. That's a logical fallacy.
No, it's not, Paul. You can't make an assertion without evidence to prove that it's true.
That's the definition of a logical fallacy.
You can't do it, Paul, unless you can prove it's true.
That is a logical fallacy.
No, it isn't, Paul. It's called asking for evidence to prove it's true.
It's not.
Unless you get
saying
evidence, Paul,
that it can't.
it's pseudoscience.
I beg your pardon, but saying that it can't because there's no evidence is logical fallacy.
But you're saying it's true without evidence. That's false.
By the very same reasoning, have no evidence to prove that it can't.
But it's your assertion that we're testing, Paul.
It's the same.
Anthony,
evidence.
Anthony, you have no evidence to say that it can't.
No, your assertion on the heliocentric model.
You have no evidence to say that it can't.
The evidence doesn't exist. You can't cite it as true unless
you cannot say that it can't.
No, Paul, you're being dishonest. You're being
I am not being dishonest. You are.
No, you're the one with the assertion. You say that we live on a ball. When we test it,
you are the one that is asserting that it can't.
No, you're the one with the assertion saying it is.
You just said before it can't.
I'm with Warrior.
Paul, you're being dishonest. With no evidence, it's rubbish.
Okay.
Can you stop screen sharing, please, Anthony, just so I can come back to the...
Well, I'm not the one making the assertion. Paul is.
Well, just let reality arbitrate. I mean, you got two composing sides. Let reality decide. Do more research. We'll find out about this in 50 years. Fine.
Well, someone's going to go away and look into it. But trust me, I've already looked into this. There is no evidence that iron can either be conductive or hold a magnetic charge when it's at the temperature that it's claimed to be at. Paul says that's not the case because...
I beg your pardon. You are now asserting that there's no evidence that it can't be conductive?
Yes, or magnetic. It doesn't conduct.
That it can't be conductive?
Yes.
Metals, by their very nature, are conductive.
Yes. But once you get to...
You do not change the metallic bonding structure by putting it under any amount of pressure.
Yes, you do. That's the application of the Curie temperature. Yes.
That is not what the Curie temperature is.
The Curie temperature is once you get beyond the Curie temperature, it loses its permanent magnetic state. Agreed?
And why is that? Do you understand why?
Because the core is hot.
No, because the Curie temperature is exceeded.
Electrons.
Do you know why? Do you know why metals lose their magnetism at the Curie temperature?
Because the Curie temperature has been exceeded. That's the answer.
No, that's not the reason. That doesn't explain why.
Oh, if you're going to start talking about molecules again, we're not going there. I'm asking you for evidence to prove that iron can do what sodium does. And guess what? You haven't got any.
Does copper have a Curie temperature?
Ding ding would be the phrase I'd be thinking. Does copper have a Curie temper? Let me look it up. How is that relevant?
To the core.
Because we use copper in generators in power stations to generate electricity by spinning it in a circle.
Curie temperature of copper.
So the core's got a copper. Okay.
Good luck with that. No, what I'm saying.
No, he's making an example about he said that only sodium can do it.
No, I'm saying sodium can do it, but Paul's saying that it crosses to everything. And I'm saying there's no evidence to say that that's true.
Copper is a non-ferromagnetic material. Anthony, don't bother looking up the Curie temperature of copper. It doesn't have one.
Too, right?
I was going to say I can't find one. And you know what happens?
Right, because there isn't one. Because there isn't one, Anthony.
Stop, Paul. Paul, you know what happens when you look something up and can't find evidence to support it being true? It generally means it's not true. Just like you've just illustrated with copper. I looked it up, couldn't find anything. It means that there isn't one. Well, guess what? If you do that with iron, same thing.
Now listen to me here, Anthony. Copper is non-ferromagnetic. Okay, it doesn't hold magnetism, and yet we use it in generators. We spin it around in circles in a self-exciting dynamo to create electricity. It creates a magnetic field, and by self-exciting that loop of copper in a generator, it creates electricity. It creates a magnetic field.
Can you prove it? Can you prove that?
Anthony?
Yes or no?
Yes, Anthony. Right. power stations generate electricity. Is that a given or not?
Yeah, but I'm asking you to prove that copper being spun creates a magnetic force. I'm asking you.
That's what it.
No,
you can buy that.
You've made an assertion, and now I'm asking you to prove that it's true.
Oh my God, Anthony!
Prove it's true.
In any generator that you buy off the shelf, it uses copper coils inside it to generate the electricity.
You said it was spinning.
That's right.
I mean, the real crux seems to be whether or not it matters if it's a solid
copper
liquid.
coils.
Those are solid coils. How about liquid coils? Can the copper liquid coils accomplish the same feat? That's the real crux with the molten iron.
Yeah, that is a question. If you were able to melt the copper and spin it like that bowl of sodium, I imagine that the same thing would happen. There's no reason to doubt that it wouldn't.
No, you would need evidence to believe that it's true. You can't just say I believe it because it makes sense because sodium does it. That's rubbish. You have to see that iron or copper does what you say it does. Otherwise, it's conjecture. So without evidence, Paul, I'll tell you what, Paul, this is what we'll compromise. You go away, and next time we run into each other, and I'll watch for you because I'll come in and I'll challenge you for it. I want to see evidence that iron is either magnetic or conductive at the temperature that it's at, according to your model.
No, it doesn't have to be magnetic.
Yes, it does.
No, it does not. Is copper magnetic? That's a straw man.
No, it's not, because it's required on the
because
temperature.
Copper is not magnetic, and yet we use it to create electricity and magnetic fields.
Right, Paul, let's go back into the definition. The Curie temperature to be replaced by
I don't
induced...
care what the Curie temperature is. It's irrelevant.
It loses its magnetism and it gets replaced by induced magnetism. Agreed?
It gets replaced. The material becomes paramagnetic.
It says on the thing there, it says replaced by induced magnetism.
That's right. If you want to magnetize it, you have to induce the magnetism with something.
Right. And then it says, once we're talking about induced magnetism, it says net magnetization results from the response of a material, in this case liquid iron or solid iron, whichever, to an external magnetic field.
That's correct.
So where would the magnetic field come from in the ball earth model?
From the rotation of the iron.
No, external magnetic field.
I need to point out something to you here, Anthony. Okay. When they generate, are you going to listen to me without interrupting? Okay.
I'm listening. Go on.
Thank you. Okay. When they generate, this is quite interesting actually. When they generate electricity at a power station, they use generators. There are no permanent magnets in those generators. What they do is they use copper coils, all right, and they run electricity through those copper coils that generates a magnetic field. They then spin other copper coils past those coils, and the spinning of those copper coils generates electricity. Okay. Some of the electricity that they generate from those spinning copper coils is fed back into the other copper coils to keep the magnetic field going. It's called a self-exciting dynamo. Okay. There's no permanent magnets in those generators. Okay. By their very nature, they self-excite. Some of the electricity is used to generate the magnetic field that the other coils rotate through, that then generates more electricity. This is the same principle that happens in the Earth's core. Okay? The convection currents that rise and fall generate an electric current, which generates a magnetic field.
Prove that point on iron.
I was gonna add there that the magnetic field of the Earth is caused by the movement of the core.
Yeah,
that's right.
Prove it though. Prove that does it to iron.
That's correct.
How you doing, Jeremy? Good to have you.
I agree with the concept.
Good morning.
I agree with the concept. I disagree that it applies to iron. So next time we see each other, Paul, find me some evidence that proves that iron is either conductive or magnetic at that temperature. That's all I'm asking. No, it's not.
In general, metals do behave in a certain way, but like you say, we might be assuming incorrectly, and there might be something different going on here. We'd have to do a hard experiment to see if there's something we might be missing. So we'll see.
But it's not liquid like water. It's liquid like sludge, like mud, or it's thick, isn't it? It's not just like water boiling down there. I mean,
it doesn't matter. It still has convection currents.
Yeah, I know. I'm just saying.
Convection currents. But Paul,
I have a feeling they think it's like water or something. I don't get it.
So can I let me just clarify? Is your position that the convection currents create the magnetism, which then feeds the core? Is that what you're saying?
Yes.
Right. So next time we speak, I want you to prove that iron does that, because there's no evidence out there that says that it does. So I want to see proof of it. I also want to see secondary.
But there is evidence.
Prove
there
it.
Is
then.
evidence. You're just ignoring it.
Prove
well,
it.
I'm looking at a study here, which is about the speed of the rotation of the core.
Irrelevant. It should be to do with iron.
Well, it is. The giant orb of iron and nickel that anchors the Earth's center is spinning faster than the planet's surface, according to a new study that confirms scientists' expectations. And this is about analysis of earthquake pairs that occur at roughly the same spot on Earth, but at different times.
So it's not relevant then?
Well, how is it not relevant? It's directly about the Earth's core and its movement.
Yeah, but
and you're asking for proof that the Earth's core moves.
No, I'm not.
It's not just proof that it moves.
No, Jem, you've misunderstood.
Hang on,
very clear.
I'm speaking.
Yeah, but
this isn't just proof that I'm speaking, Anthony. You stop speaking, okay? This isn't just proof that the Earth's core moves. This is proof of how fast it moves.
Fine. That's not the issue. The issue is, does iron conduct or become magnetized at that temperature? Yes or no?
Why are you saying that iron doesn't conduct at that temperature? All metals conduct.
Because it's supercritical. At that temperature, iron doesn't do it.
What do you mean by supercritical, Anthony?
It's gone past the critical point.
What's the critical point?
It's the point where it becomes like it becomes like the fucking sun, man.
What's the
supercritical means? The supercritical means that it's so hot that it expands even more than it does at the gaseous stage, and the only thing that's keeping it in the liquid stage with all that fast atomic movement is incredible pressure. Without that pressure applied, it would evaporate off and would not be in any sort of liquid state. So it's a liquid that is a high temperature liquid that's kept liquid by incredible pressure.
Saying about it being like a sort of reverse, like it goes to gases on the inside, so it's like a hollow core of gases, but
so let me dense. Just again, for the avoidance of uncertainty, let me be specific with what I'm asking. I'm asking for evidence that proves that liquid or solid iron at the temperature claimed, which is about 7,000 degrees, is either conductive or magnetic at that temperature.
All metals are conductive by their very
temperature
structure.
At that
regardless of temperature, they are conductive.
So, Paul, as a physicist, I would expect you to be able to find the evidence relatively easily, but maybe a week or so, it's fine, but come back with that proof. Without that proof, that core's not made of iron, if it's there at all.
If you choose not to believe it,
I don't believe it.
It's irrelevant to reality, Anthony.
No, but Paul's saying it's true.
You need to remember that. No one cares if you just decide to reject evidence that's supported by science.
But people do care that there's assertions without proof. So what I'm saying is,
and as rigorous reviewers of the science, we have to see if the science has been derived from theories or hard observations, a video, something that's observable.
You know what theories
I just described to you some of the
and
observations, didn't I?
Define theories.
Support
say a mathematical formula that you expect or something like that, or based off of this a law that somebody else says. We're going to make these formulas, we're going to make these mathematical equations, but no samples, no hard evidence, nothing you can touch, nothing that you can observe.
Okay, but I just told you about some hard evidence, didn't I? I just gave you some examples of it.
To do with the movement of the Earth.
So that's
the movement's fine,
meaningless.
Right. Let me put it into context for you. Right.
I heard it, Jim.
This illustration was done with sodium, and the sodium's got a melting point of around about 90 degrees, give or take. That's quite easy to obtain. It's not that difficult to do, but it's not supercritical. So it remains conductive and it remains magnetic. At a it's when it's not.
Why are you pretending that you know about this stuff?
Because I've researched it.
There is absolutely no reason to believe that any metal will become non-conductive under any conditions.
No, there's no evidence to assert that it's true. That's the problem. You're applying and accepting logical reasoning, and I'm asking for the proof that a supercritical metal in its liquid or solid state can be conductive or magnetic at the temperatures claimed. And there is none, because I've looked heavily into it with a lot of people. So I'm asking as a physicist to go and find the evidence to prove that that's true.
The sun has risen for the past 4.5 billion years every day. You've got no evidence to prove that it's going to rise tomorrow.
You've got 10 minutes. 10 minutes.
Just get the evidence, Paul. I've been really clear and concise.
So that LIGO, measuring gravity and stuff, 4 kilometers straight, is it?
I don't know what
and magically managing to do it right when they needed funding, probably. I'm calling BS.
So your Google research is on par with Paul's education and all the years he spent. Is that what you're saying right now?
Me?
Yeah.
I'm saying that there's no evidence that a supercritical fluid or a supercritical solid can be magnetic and conductive at the temperatures that we're told.
And how do you know there's no evidence?
Because there is none. I've been looking at it for the last 2 weeks, and I've had 2 hangouts on it, and there's none been produced from either opposition. One was GeoStreamer. Wait, I'm talking. One was GeoStreamer, the other one was Miles Davis. Neither of them got evidence to show that this was true. So now Paul's a physicist. He should be able to do it.
So all that is required to conclude that a piece of data does not exist in the world is for you to hold 2 hangouts and look into it for 2 weeks.
No, all that's required.
From that, you can reach the conclusion that something that you isn't a field that you know about, you don't have a background in, that you can make conclusions about what it does and doesn't know, or what is.
If I was wrong with my conclusions, Paul would be correct.
2 hangouts.
Paul would be quick to correct me on the physics. What I'm quick to correct Paul on is the evidence, because a supercritical fluid cannot be conductive or magnetic at that temperature.
Now let's talk about this notion of evidence, Anthony.
Yeah, go on.
The sun has risen for the past 4.5 billion years every day. You have no evidence to prove that it's going to rise tomorrow.
I'm not certain that it will rise tomorrow.
That's the kind of bullshit that you're going through right now.
No, it's not, Paul.
Yes, it is.
I'm very clear with what I've said to you. A supercritical fluid.
And it's bullshit.
Right, because there's no evidence to prove that it's true.
That's right. What you have done is you have taken the entire body of scientific knowledge and poo-pooed it.
No, I've just simply asked for evidence that the core...
You have taken
No, I haven't. I've asked for evidence that the core is what they say it is.
You have taken everything that we know about metals, that metals conduct under every situation that we have possibly been able to put them in. Metals
Let me put it into context for you then, Paul. Make it easier. When they dug the Polar Bore Mine,
under every situation we have put them through, and you're saying, but
listen. Let me put it into context. When they dug the Polar Bore Mine, what came out of the hole was boiling hydrogen, not iron, not magma. It was boiling hydrogen. Now that makes me think that there's a lot of hydrogen down there. Now hydrogen can be conductive and magnetic, but iron cannot.
Hydrogen.
It's more to do with the composition.
Boiling hydrogen?
Yeah, boiling hydrogen came out the hole.
What are you talking about?
Do you want me to get the evidence to prove it?
Yeah, please. Let's see it.
Give me a minute. Give me a minute.
I didn't know hydrogen was a liquid.
Boiling hydrogen it was. Let me go back. Let me find it. Give me a sec. I think it might be this one. No, so it must have been the one underneath it. Or maybe it was it's one of these 3. Hang on. Let me search for it. Control and F. Boiling. Here we go. Another unexpected discovery was a large quantity of hydrogen gas. The mud that flowed out of the hole was described as boiling with hydrogen. Yeah, interesting that it wasn't iron, right?
Huh? Oh, come on, Anthony. Are you trying to tell me that drilling 12 kilometers down, you would expect to get to the iron core of the Earth?
No, but I'd expect there to be a lot of evidence of iron.
Seriously?
I would expect there to be evidence to support the notion that iron is down there.
Oh, not at 12 kilometers, Anthony. You know that that's
it's
bullshit.
The deepest hole that we've ever dug.
So why what? We know that the iron
it's nowhere near the core of the Earth, is it? It's not even close to the core of the Earth.
It's not even close.
I told you that it was boiling with hydrogen. You laughed at me. I've now given you the authority.
So with that, I'm probably going to round out the show a little bit early. So first and foremost, a massive, huge, enormous thank you to all of our live audience for joining us on this live debate. And of course, a massive thank you to all of the panel members for making this debate possible. Be sure to like, comment, share and subscribe. I've been Nathan Oakley and I will see you all in the next video.